So today we're going to take a look at a little bit of supplemental material. If we can, if we have time, we'll take a look at it in class as well. But I want to make certain that some of these key ideas, especially with calculus, are available in a format that you all can come back and double check at your leisure. And also so that people who may not have had the same level of calculus, they can come back after they've actually gone through some of it and are a little more comfortable with it. Today we're going to take a look at least starting off, some capacitance. So we've been using Gauss's law in class to actually find things like the electric field around different objects. Sometimes we'll follow it up by seeing what the capacitance is. And what capacitance really is, it's a way of rating how much energy and charge we can store onto a given object. In particular, if you have not had the equation introduced, then we end up with the following. And now, it may be written in a couple different formats, but the one that I always remember is Q equals delta V times C, or QVC is how I usually kept track of it before I paid extra careful attention about the delta for delta V. QVC, if I'm not mistaken, at least was, and probably still is, the abbreviation for the home shopping network, where you can go to charge things on a card, among other things. You can laugh all you want, but I've never had to look up the equation because I remember it this way. Mnemonics help. Regardless, C is what we're actually after here. It's called the capacitance. And it describes the energy and charge stored on a capacitor. Now we're going to work with that a lot more when we get to circuits. We're going to have capacitors as circuit elements, components, and we're going to be working with their capacitance. Here is where we're actually going to find how you can calculate those things. And they're going to be based off of some of the relationships that we've done before. I'm going to start us off. We're going to look at two of them, basically two examples. One is a very simple case, and the other is a more complicated application of that same simple case, but one that we can actually use the first to double check. Biggest thing is this. Capacitance is defined. In fact, the better way to write this equation, though it's a bit less memorable, is the capacitance of a capacitor is defined as the charge on the capacitor divided by the potential difference applied to the capacitor, aka the voltage across the capacitor. Now, here's something to keep in mind, because usually when we talk about capacitance, it makes you think, oh, well, that's the total amount of energy or charge that can be stored on a capacitor. That's not always the case. There is a limit to how much you can store on a capacitor, but the important thing to note about this is how much the capacitance is not only a function of the total charge, which you'd think it would be describing, but it's also a function of the potential difference. So we're going to find for a given capacitance, the total amount of charge it can hold will depend on the potential that we put across it, the voltage. More potential difference, more voltage, we can push more charge onto it. So that's something to keep in mind. I know when I first worked with it, I kept thinking of capacitance as basically the total amount of charge you can store on there. That's not technically right, because the amount of charge will change as a function of the potential difference across it. That being said, it still describes the relationship between the charge on the capacitor and the potential difference across it. And that is going to be a function of how we build the capacitor. Now, the main capacitors that we use, and the number one thing that you're going to find, say, on the AP exams equation sheet, is a parallel plate capacitor. Those are ones that we've worked with quite a bit in class, where we end up putting a bunch of positive charge on one side, and we end up with negative charge on the other side. We end up with a nice uniform field, uniform and constant field between the two plates. And, as we may or may not have talked about in class, not to complicate things, but we can change the capacitance by inserting something called a dielectric, some material that will change how the electric fields go through here. Oops, that's not what I want. Good enough. If you put a dielectric in here, it will change how the electric fields go through there, and it in turn will change your capacitance. How does that come into play? We'll see as we start developing it, though I'm not actually going to include a lot with the nature of the dielectric constant, which is a different epsilon value or is usually defined as kappa. It's another Greek letter. Anyway, before I get too lost on a tangent, the regular capacitor we look at is this, and I don't have the sheet on me, but there is a capacitance equation for it on the AP equation sheet. I believe it's equal to something like kappa times the area divided by the separation distance, where this is D, the plate area is the area of one of the plates. There should be a kappa in there for the dielectric constant if you insert something else, and there may be something else I'm going off of memory here, and it's been a little while since I worked with that. Anyway, right now we're not going to derive that. I believe we did derive that in class. We're going to look at a different charged object. Let's take one of the simplest ones that we can work with, a spherical conductor. And I'm going to put a total charge on it of plus Q. Now, since it's a conductor, that Q is actually going to be on the outside edge of the conductor, which is fine. So we've got a ball, and all the positive charges are spread out on the outside edge. That gives us inside, the electric field is equal to 0. We're going to say that this sphere has spherical shell or sphere doesn't actually matter because in this case, all of our charge as a conductor is going to be on the outside edge. We're going to call its radius A. So what we would normally do in class, big R, is now just some value A. If the distance r, little r, is less than A, then the electric field, as we find in class, is equal to 0 Newton per Coulomb. We have no enclosed charge. Now, I'm not going to go through and apply Gauss's law, although I am referencing it. So if we had a Gaussian bubble on the inside, there's no enclosed charge, so we have no electric field. On top of that, we've talked about this in class. Inside a conductor, the electric field is equal to 0. So let's look outside. Now we could go through and apply Gauss's law. That's something that we've done quite a bit. However, I'm going to take the takeaway answer from that. And hopefully when you look at this, you think, spherical distributions of charge act a lot like point particles. And we should find that for little r greater than A, that the electric field will be equal to K, Coulomb's constant, times Q, the charge, which in this case is positive capital Q, divided by r squared, where r is whatever distance away we are. Now, in vector notation, with this being positive, my electric field would point out in all directions, so I could also tack in here an r hat direction. If it were a negative Q, then I would have a negative there, and it would point in the negative r hat direction, which means instead of pointing out, it would all point in. So here's where the negatives work out in our equation. That being said, we're just going to take the magnitude, which is KQ divided by r squared. For us to find the capacitance, we need to know about the charge on the conductor and the potential difference. We're going to see how to calculate that. First off, the charge, well, we already know the charge. It's positive Q. That's how much I put on this capacitor. So let's find out what the potential difference is for this particular distribution. To do that, I need to use the following relationship. V equals negative integral E dot dr. Now this is an important one. We've mentioned it a couple times in class, and it's a fundamental relationship. I'm going to remind you of this, that in the grand scheme of things, we found that the potential energy was basically us taking the negative of work done by a conservative force. So for gravity, if I lift something up, gravity is doing work. There's a force of gravity pointed down, and my displacement is upward. The angle between them is 180 degrees, which means cosine of 180 gives me a negative. The work done by gravity as I lift this up is a negative value. Gravity is stealing my energy. Now that's if gravity is not part of your system. To make things easier on us, because there's a very predictable equation that goes along with gravity, what we did is we said, instead of looking at it as though gravity is stealing my energy, since it's going to give it back when I let go, it'll give the same quantity back. It will apply a force downward, this falls downward, and it will do an equal amount of work. It gives that energy back. We said instead of saying that it steals my energy by doing negative work, we're going to say that it does positive. It's storing a positive amount of potential energy. This is the relationship between potential energy and work. Potential energy is predictable work done by a conservative force. Now, conservative forces, gravity, as I lift up, I have gravity stealing energy. I apply a force upward over a displacement, I put energy in, but this doesn't speed up, it doesn't gain any kinetic energy. So the energy is going somewhere. Turns out gravity is stealing it, or if we redefine our system, we say that gravity is holding on to it for us. All right. So that gives me the following, that my potential energy is equal to negative the integral of F dot dx. My potential energy, we talked about this in class. Remember that the potential is equal to the potential energy divided by the charge, and that the electric field is equal to the force divided by the charge. So with this equation, if I divide both sides by charge, I end up with the following. My electric potential is equal to negative integral E, force divided by charge, is my electric field. Potential energy, in this case electric potential energy, divided by charge, gives me my potential. Dot dx, or as we're about to use, because we're not looking in the x direction, we're looking in the radial direction, the r direction. So it goes out in any radial direction. For the most part, there isn't much of a difference. We're just integrating along one dimension that's moving in a straight line here. All right. Here's where we get that equation from. It should show up on the AP equation sheet or one very similar to it. They may have it in the differential form, but every time I introduce it, if it's been a while since you've seen it, I do want to draw these connections. They're all based off of definitions. Potential energy is predictable work that can be done or will be done by a conservative force, and these relationships will carry us through. I remember this relationship because of these, this, and this. Whether or not you want to do that or just be aware and use it along with the equation sheet is entirely up to you. Okay, now that we've got this, I need to find the potential difference. So, my potential difference, specifically delta V, is going to be equal to negative the integral from, here's what we're going to do. We're going to integrate the electric field, its effect, from one point to another. Well, we know that we want to get to the surface of the sphere, so we're going to integrate all the way up to A, but we need to start, well, realistically, you may not realize this, but we need to start infinitely far away. Technically, I'm going to integrate and find the actual potential, not delta V, the potential difference, but here's what I'm going to do. I'm going to integrate from infinitely far away to a distance of A. I'm going to integrate the electric field dot dr. Now, the reason that I do this, V infinity equals 0 volts. This is by definition. I've mentioned this in class and in other locations. With equations like this, we've actually set a common potential reference point. It is infinitely far away, and we say that that is at 0 volts. Technically, I can drop the delta on this. We're going to see that both of those are going to be the same because my lower limit is actually going to be 0 volts. So this is going to tell me what the absolute potential is, the total potential, and it's also going to happen to be the potential difference that's actually on the sphere itself. In the next example, we're going to see that we have to do a potential difference because I'm not going to do it with reference to infinity. All right. My potential is going to be equal to negative integral from infinity to A of the electric field, which we said was KQ over R squared dr. Now, real quick, I dropped my vector signs and the dot product. The electric field for this positive points outward radially in each direction, and I'm going to be integrating, from infinity into A, so I apologize, I do actually need something here. When I evaluate my dot product, the direction that I'm integrating in is actually inward, but this is pointed outward, so I end up with the dot product returning a negative, which is a second negative, which is going to cancel that out and make this positive. I think. Let's double check that. Anyway, for now, let's go ahead with that. I think, because we're integrating from infinity inward to A, so we should be, our displacement is going inward. The electric field points outward, we're displacing inward, so we should have a negative in there. We'll double check, I may have misplaced a negative, but let's still see what we come up with. V, the absolute potential, is going to be this. We end up with K and Q are both constants, and we end up with the integral from infinity to A of dr over, r squared. R squared. Yeah, I'm wondering if I've misplaced a negative in here. I apologize, I may have made that a little bit more complicated, because I think we're going to end up with a negative when we should not end up with one. I think I've reversed the integration directions. That's okay. Here, at the last step, I'm going to bring in one thing that's going to eliminate our problems, although it's a little hand-wavy. I apologize, I think I may have misplaced a negative, but that's all right. So I'm going to end up with KQ times, the integral of dr over r squared would be negative 1 times 1 over r evaluated from the lower limit of infinity and A. So I would end up with this, negative KQ times the quantity of 1 over A minus 1 over infinity. This will be equal to my potential. 1 over infinity. The limit of this approaches 0, and even if it didn't, what I'm actually saying here is that I've got VA, or I'm sorry, the potential here is going to be VA minus V infinity. This, as I said, we start at infinity and come into A is the same thing as saying V final minus V initial, which is, by definition, delta V, which is why I showed the delta V earlier. The other thing about delta V is it's showing the potential difference here, but neither here nor there. The most important part of this is, whether you like this approach or not, remember VA is a value and V of infinity is by definition 0 volts. So even if you're not fond of this, that 1 over infinity only approaches 0 and is not technically equal to 0, when we actually write out what this is, my potential is VA, specifically my potential difference, is VA minus V infinity, and that we, the scientific community, have defined V evaluated at an R of infinity to be 0. This whole term must be 0. All right, we end up with the following. And I think I did end up with a negative in here, but the delta V should actually account for that. We end up with negative KQ over A. If you remember, A is also equal to R, so we'd have KQ over R. I'm sorry. Yeah, so A would be equal to the big radius there. And then we end up with an equation very similar to what you saw for the potential for a sphere. Spherical distribution is KQ over R. Not R squared, but R. All right. I think I may have misplaced a negative in here. That's kind of evident. Even with the delta, I can just drop the negative, but it's still not necessarily nice. I'll see if I can track it down. I'm willing to bet that I'm not thinking of this correctly with the dot product evaluation there. Because with a positive Q, a positive charge, we should end up with a positive potential here. Let's see, my initial would be 0 really far away, and my final would be a positive number. I should end up with a positive number. I apologize. I think I've got an extra negative in here from the dot product. One thing that I can say on this is that with the delta V, the potential difference, a lot of times we actually don't pay too close of attention to the positives and negatives, because you could also say that the potential difference, it's either negative this way or positive that way, but if you're looking at the difference the other way, it can switch signs. That's one of the reasons why many times we will only find delta V. I'm about to get us set up for the second one. In fact, let's go ahead and take a look at it now. We're going to find that we don't measure, or we don't find the actual potential itself. We are only finding a potential difference. Here's what we're going to do to step this up. A. B. We're going to say this, that we have nested conductors. I'm going to do positive Q on the inside, and we're going to end up with a negative Q over here. I want to find the capacitance of this setup. Basically, two conductors. We've got a spherical conductor here and a spherical shell around it. The inner one has a radius of lowercase a, and the bigger one has an inner radius of lowercase b. Now, if we find the electric field inside less than a, we know that that's going to come up to 0. If I find the electric field here using Gauss's law, we're going to find that it actually ends up being the same thing, although this time we're not going to integrate from infinitely far away because I've not given us information about the entire outside shell. What we are going to do is we're going to integrate inward from B into A. So all the stuff that we talked about before, oh, I'm sorry. Here I am forgetting important stuff. So delta V is equal to KQ over A. And what we were actually after is the capacitance, which is equal to Q divided by delta V. Well, that would be Q divided by KQ over A. I'm going to flip A back up here, and we end up following. We end up with A divided by K, where K is Coulomb's constant. Another way of writing all of this would be 4 pi epsilon naught. Here's the permittivity of free space times A, where A is the radius. That is the capacitance of this sphere. I apologize, forgot the last step there. All right, back on this one. We're actually going to end up with something very similar. I'm going to save us a little bit of time here because this is already starting to run a little long. Delta V is going to be equal to, should be negative, but again, the delta is going to cause that to drop. Negative, we're going to integrate from B, out from B, all the way in to A. Or we could do from A out to B. We could switch our limits of integration by multiplying by a negative. In this case, E dot dr, we're integrating inward, so we'd end up with a negative that comes out there. Again, if we switch our limits of integration, that would introduce one more negative, and so we should end up with either way you want to set it up. I'm going to set it up this way, although I think I might drop the negative on this for the delta V, just so we see if it's going to come out the same way that it did before. In short, we're going to end up with the following. Delta V, and this one is emphatically delta V. It will not be the actual potential. For us to find the actual potential, we would have to somehow start off at infinitely far away and set it equal to 0. If I gave you more information about the outer shell, we could come in from infinitely far away knowing that it is absolutely 0, and whatever we find on the outside shell, let's say 6, then that would be 6. And then we could find the potential difference from here, 6, into whatever this is. We would add on the delta V that we are finding here. That's how you can go about finding the absolute potential. In this case, I'm only looking for the potential difference, delta V. All right, so we're going to call this from B to A of our electric field. Again, the only thing in charge is Q. So we've got KQ over little r squared dr. We end up with more or less the same thing that we saw just a moment ago. We're going to end up with, there's a negative that comes out, we'll more or less drop it, but negative KQ times 1 over r evaluated from B to A. All right, again, the negative on this, we're finding a delta, so if we were looking from here to here or here to here, it would introduce a negative. We could switch our limits of integration like this. I think I've got one too many negatives in here already, but that's neither here nor there. Clearly, I'm having a problem with negatives right now. I apologize. I had it written out, but I think I turned myself in circles. Regardless, delta V is going to be something either positive or negative, akin to KQ over or times the quantity of 1 over A minus 1 over B. Here's where the negative is probably actually important here. A is a smaller number than B. No, I apologize. Again, I'm turning myself around with the negatives. But A is a smaller number than B, so 1 over A is a bigger number than B, and so this becomes a positive value. We should actually increase. We know that the negative side is going to be more likely to be on the negative potential, and so as we go across here, we will actually increase. We should end up, if we're going from here as our initial and here as our final, we should end up with a positive delta V. Here's where, even if you misplace some negatives, you can account for that by taking into account what you've got. This is going to be at a lower potential, and this is at a higher potential. So if I'm going from here into here, I should have a positive delta V. If, however, I go from here to here, I'm going from a high potential to a low potential. How do I know that? If nothing else, if I put a positive charge in here, it will run away from this and towards that. So we end up with from high potential to low potential. So delta V is actually this. So if I want to find the capacitance, which is Q divided by delta V, that'll be Q divided by KQ times 1 over A minus 1 over B. Our Q's actually cancel out, and we end up with this. 1 over K, 1 over A minus 1 over B. Or it could also be written as 4 pi epsilon naught over 1 over A minus 1 over B. Here's our capacitance of the nested structure here. We've got a conductor with positive Q and a spherical shell, a spherical conductor here and a spherical shell here around it. Here's where we tie these two together. I originally had just this one. What you can do is we can take an approximation. Let's say we've got the inner one that is definitely still at a radius of A, but let's say that the outer one, let's make it so big, so far away, that instead we say that B goes to infinity. In other words, we now make this other shell so big that the edges are so far away that it's effectively like it's not even there anymore. That is the same thing as this, except we've got the spherical shell way out there, so far out that we can't even imagine it. If that's the case, what happens when I take the limit as B goes to infinity? Well, if B goes to infinity, as we talked about before, little iffy mathematically, then this goes to 0, but we end up with the following. Oops. Oh, that's fine. Different color. 1 over 4 pi epsilon naught over 1 over A, and we end up with 4 pi epsilon naught times A, which is the exact same as what we got the other way. Once again, I apologize for some misplaced negatives. I'll see if I can get those fixed up. But there you go.